Good morning, everyone. My name is Aditya from BSc Chemistry Honors Final Year. Today, I am here to share the video of my audio presentation of the topic fats, oil, and detergents for the visually impaired student. So, let's start with the introduction. Oils and fats are widely distributed in the nature both in animal and plant kingdoms. In animals, they are present under the skin and in muscles, but in plants, they are mainly found in the seeds. Some important examples of fats are butter, lard, tallow, beef, etc. While groundnut oil, cottonseed oil, olive oil, palm oil, coconut oil, sunflower oil, soybean oil, linseed oil, sesame oil are some important examples of vegetable oils. Fat and oils are one of the three major constituents of our food. The two other being are carbohydrates and proteins. In fact, fat and oils serve as energy reservoir for the animals. In human beings, only a few hundred grams of glycogen can be stored, which can barely supply the food's energy needs for about 12 to 18 hours. In contrast, large amounts of fats 12 kg for an average person weighing 70 kg can be stored, which can supply the body's energy needs for about 8 weeks. Besides this, oil and fats serve as raw material for a number of industries such as soap, paints, varnishes, and vanaspati ghee. Natural fats. The fats which are obtained from the animal sources such as butter, lard from hogs, and tallow from sheep, goats, etc. are called natural fats. This name is simply given to differentiate these fats from those fats which are obtained by the hydrogenation of oils. Edible and non-edible oils. On such oils such as groundnut oil, sunflower oil, soybean oil, rapeseed oil or mustard oil which are used for cooking purposes are known as edible oils, while oils such as cottonseed oil, linseed oil, castor seed oil and mahua oil which are used in soap, paints, varnishes and liquor industries are called non-edible or industrial oils. On the basis of iodine values, oils have been classified such as drying, semi-drying and non-drying oils such as in section 9.7. Industrial oils may include essential oils or mineral oils. Essential oils such as rose oil, jasmine oil, lavender oil, eucalyptus oil, and peppermint oil are the volatile oil isolated from the plants. Essential oils may be hydrocarbon, alcohol, aldehyde, ketones, ester, but esters are not of glycerol. For example, peppermint perfumes, cosmetics, menthol and its chief constituents. Essential oils are mainly used in the perfumes, cosmetics, and in pharmaceutical products. On the other hand, mineral oil such as paraffin oil is a mixture of saturated and unsaturated hydrocarbon and not esters or triglycerides. They can't be saponified. They are called oil simply because of their physical appearance. They are non-edible and are mainly used as the fuels. Triglycerides, composition of oils and fats. As stated above, fats and oils are the triesters of the glycerol with higher aliphatic monocarboxylic acids. In other words, they are the triacyl glycerols and are commonly known as glycerides. Fats and oils may be represented by the general formula shown on the screen where R, R dash and R double dash may be same or different alkyl groups. Fatty acids. With the only few exceptions, all the monocarboxylic acids isolated from the fats and oils are straight chain compounds containing 3 to 18 carbon atoms. Further, with the exception of only C3 and C5 acids, all other acids are found in the fats and oil contains even number of carbon atoms. The chief saturated fatty acid present in oil and the fat are lauric acid, myristic acid, palmitic acid, and stearic acid. Besides saturated fatty acids, unsaturated fatty acids containing one or more double bond in cis orientation may also be present in oils and fats. The chief unsaturated fatty acid present in oils and fats are oleic acid, linolenic acid. Classification of glycerides. The three fatty acids in glycerides may be same or different. Therefore, glycerides are classified as simple or mixed glycerides according to they have the same or different acid residue. For example, tripallitin or glyceryl tripallimitite or the alpha illio beta pallimito alpha styrene, that is a mixed glyceride. Glycerides are further classified into the saturated and unsaturated according to they contain saturated fatty residue or unsaturated fatty acid residue. For example, tristyrene is unsaturated triglyceride or triolene is an unsaturated triglyceride. Both of simple and mixed glycerides are found in natural oils and fats. In fact, oil and fats are the complex mixture of mixed glycerides along with small amounts of simple glycerides. Chemical difference between oil and fats. The main difference between the oil and fats is the proportion of saturated and unsaturated glycerides. The triglycerides with higher proportion of saturated acid residue such as palmitic acid, stearic acid are the solids at ordinary temperatures and are called fats, while those with the higher proportion of the unsaturated acid residue such as oleic acid, linoleic acid are the liquids at ordinary temperatures and are called oils. Melting point of glycerides. As stated above, fatty acids have one or more double bonds having the less stable stereochemistry. For example, oleic acid has one cis double bond at C9 position. Linoleic acid has two double bonds present at C9 and C12 position, and while linoleic acid has three cis double bonds present at C9, C12 and C15 position. These cis double bonds have vital biological importance in the solid state. The molecules of saturated fatty acid fit closely in the crystal lattice due to their zigzag tetrahedral structures. On the other hand, cis unsaturated fatty acids have band at a double bond and hence do not fit closely there while lowering their melting points. Chemical properties. Fat and oil being triesters of glycerol, so all the reaction of the simple esters. In case the glycerides contain the unsaturated fatty acid residue, they are also show the usual addition and oxidation reaction of the alkenes. Some more important reactions of fat and oils are given below. First one is the hydrolysis. First, fats and oils are readily hydrolyzed by the treatment with the superheated stream mineral or alkalis to form the glycerol and fatty acids. Hydrolysis can be superheated steam by mineral acids give a mixture of fatty acid and glycerols. However, when the hydrolysis is carried out by alkalis, glycerol and salt of fatty acids are formed. Since the salt of higher fatty acids thus formed are as soaps, the alkaline hydrolysis is commonly called saponification. In the digestive system of the human beings and animals, fats and oils are hydrolyzed, glycerols and fatty acids by a number of enzymes called as lipases. Second reaction is hydrogenation. Oils which contain a higher proportion of the unsaturated glyceride adds on hydrogen in the presence of finely divided nickel as a catalyst to form as the solid fat. For example, triolene is converted to tristyrene. This process is called hydrogenation or hardening of oils. It is similar to the catalytic hydrogenation of alkenes and involves the reduction of double bonds present in the unsaturated glyceride to form the saturated glycerides. This process is extensively used for the manufacture of the vanaspati ghee, such as dalda, rat, and gagan, for groundnut, peanut, and sunflower edible oils. Hydrogenation is never carried out to the completion but is stopped as soon as the fat is consistently comparable to the ghee is obtained. The completely hydrogenated fats are too hard to be useful as kitchen shortenings. The main advantage of hydrogenation is that compared to oils, fats have better storage qualities, and do not become rancid easily. Hydrogenolysis, that is the conversion to alcohols. Fats and oils on treatment with the hydrogen temperature and pressure in the presence of copper chromite as catalyst undergo reductive cleavage to form and glycerol and long-chain aliphatic alcohols. For example, tristyrene is converted to glycerol and N-octadecyl alcohol with the reaction of copper chromite. The splitting of a fat or a oil to glycerol and a higher long chain alcohol by hydrogen is known as hydrogenolysis. The long chain alcohols thus produced are used to manufacture of the synthetic drugs. Fourth reaction is trans-esterification. Fats and oils can be converted into the simple esters of carboxylic acid, such as methyl esters, ethyl esters, etc. by trans-esterification. It involves the treatment of a fat or an oil with the large excess of a suitable alcohol in the presence of acidic or basic catalyst. For example, alpha ilio beta stereo alpha palmitate with reaction of methanol gives the glycerol and the mixture of methylolate, methyl stearate and methyl palmitate. The process of trans-esterification is quite useful for the large-scale preparation of the long-chain fatty acids and the long-chain primary alcohols of high purity. For this purpose, the mixture of methyl esters obtained by the trans-esterification is subjected to fractional distillation to separate the individual esters. These upon hydrolysis yield fatty acids of high purity. Alternatively, the individual methyl esters are reduced to get long-chain primary alcohols. Fifth reaction is the addition of halogens. Like alkenes, unsaturated glycerides add halogens across the double bonds to form the addition products. The addition of iodine is usually carried out by treating the fat or the oil with the iodine in the presence of mercuric chloride as catalyst. Sixth reaction is rancidity. When fats and oils are exposed to the warm air or moisture for a long time, they develop a disagreeable smell and taste. This process is called rancidity and involves the hydrolysis of esters to produce the fatty acid and oxidation at double bonds to form short chain acids and aldehydes. These short chain acids and aldehydes are volatile and have the offensive smells. Therefore, they impart unpleasant odors to fat and oils. Rancidity is of following two types. Hydrolytic rancidity, it is caused by the liberation of the lower fatty acid by the hydrolysis of triglycerides. For example, when the butter is exposed to the warm air and moisture, the hydrolysis of the glyceride in the butter yields butyric acid and the other volatile acids such as caproic acid, carpic acid with the unpleasant odors. Second reaction is the oxidative rancidity. This type of rancidity is caused by the oxidation of the unsaturated triglycerides by air to form the short chain acids and aldehydes having the unpleasant smell. It is believed that the ester linkages are hydrolyzed to yield unsaturated acid which undergo oxidation at the site of the double bond to produce short chain acid and aldehyde. For example, oleic acid is converted to pelargonic or azelaic acid. Analysis of fats and oils. Fat and oils are extensively used in a number of industries. Therefore, it is essential to check the quality of a given fat or oil. This involves the determination of the physical constants such as melting point, specific gravity, refractive index, and or chemical constant of such as acid value, iodine value, saponification value, Richard Mesley value, etc. Some important chemical constants are discussed below. The first one is the acid value. It is defined as the number of milligrams of potassium hydroxide required to neutralize the free fatty acid present in the 1 gram of a fat or an oil. The acid value is a measure of the free acids present in the given fat or oils. A high acid value indicates that the given sample is the fat or oil is quite old and has become rancid. Saponification value. It is defined as the number of milligrams of potassium hydroxide required to completely saponify the 1 gram of fat or oil. In other words, it represents the amount of potassium hydroxide in milligrams required to neutralize the fatty acid formed as a result of complete hydrolysis of 1 gram of the fat or oil. The The third value is the iodine value. It is defined as the number of grams of iodine that will combine with the 100 gram of the fat or oil. Iodine value may be determined by any method. First method is the Hubel's method. In this method, a solution of a known weight of the flat or ion in the carbon tetrachloride is allowed to react with the known excess of a standard solution of iodine in ethanol in the presence of mercury chloride as the catalyst. The unreacted iodine is then determined by titrating it against the standard sodium thiosulfate solution using starch as indicator. For example, the iodine value of the triolane may be calculated as follows. The second method for calculating the iodine value is the Wid's method. In this method, a solution of the more reactive iodine monochloride in the glacial acetic acid is used in the place of the iodine and mercury chloride. A known weight of oil fat is dissolved in the chloroform with solution, that is, the iodine monochloride in the acetic acid is then added. ICl adds across the double bond, the ICl left behind and then treated with the potassium added solution to replete an equivalent amount of iodine. The liberated iodine is then titrated against the standard hypo solution using the starch as indicator. The amount of the iodine monochloride that is added across the double bond is then determined using the formula, that is the iodine value equal to V1 minus V1 minus V2 multiplied by N into 12.7 upon W, where V1 is the volume of hypo used for the blank titration and V2 is the volume of hypo used for the unreacted iodine monochloride, and the N is the normality of the hypo solution used and W is the weight of oil taken. Fourth one is the RM value or the Richard Missile value. It is defined as the millimeters of 1 gram of potassium hydroxide required to neutralize the steam volatile fatty acids obtained by the complete hydrolysis of 5 gram of fat or oil. To determine the Richard Missile value, a known weight of the fat or the soil is completely saponified with the alkali. The resulting solution is then acidified with dilute H2SO4 then subjected to the steam distillation. The distillation is which contains the volatile acids is then titrated against the 0.1 normal KOH solution. Then the RM value is calculated as follows. The volume of the 0.1 normal KOH used for the neutralization multiplied by 5 upon the weight of the fat upon oil taken. Industrial oils or the vegetable origin, that is the drying oils. Certain oils such as linseed oil, perilla oil, etc., when exposed to air in the thin layers, form hard and tough water-insoluble solids. This process is known as the drying, and such oils are known as drying oils. Oils like olive oil, groundnut oil, which do not dry on exposure on air, are called no-drying oils, and those which dry slowly, such as cottonseed oil, are called semi-drying oils. Chemically drying oils contain a high percentage of unsaturated glycerides as shown by their high iodine values. On the other hand, non-drying oils have low iodine values while the semi-drying oils have the intermediate iodine values. For example, drying oils having the iodine values above 150 and non-drying oils having the iodine value less than 100, and the semi-drying oils having the intermediate iodine values between the 105 and 114. Unsaturated glyceride contains linoleic acid and linoleic acid as the unsaturated fatty acid residues. These acids contain 2 and 3 isolated double bonds respectively. In general, the drying oils containing unsaturated glycerides with the conjugated double bond dry more rapidly than those containing the isolated double bonds. Drying oils are used as the medium for the paints, varnishes, and the lacquers. In fact, the paints are the suspensions of some pigments of the organic coloring matter in the linseed oil to which the some terpenotic oil has been added to as a thinner. When these paints are applied on any wooden or iron surface in thin layers, they quickly dry up to form a tough organic film which protects the surface from being painted. Now see what are the soaps. Substances like soaps and synthetic detergents which concentrates at the surface of the solution or the interface form the surface films, reduce surface tension of the solution and help in removing the dirt and dirt by emulsifying the grease tree are called the surface active agents or surfactants. The molecule of the surfactants contain the two characteristics group, one of which is water soluble, that is hydrophilic, and one is the oil soluble, that is hydrophobic or the lyophilic. Soaps are the sodium or the potassium salts of higher fatty acids such as palmitic acid, stearic acid, and oleic acid. These soaps are generally obtained by the hydrolysis of oils and fats with the aqueous alkalis. The process is called saponification of oils and fats. The fats and the oils commonly used for the soap manufacture are tallow, lard, olive lens, red mahua oil, rapeseed oil, coconut oil, and palm oil. Soap containing 12 to 18 chains atom having the good cleansing action. Soap with the 12 carbon atoms are comparatively soluble in water, whereas the soap containing 18 to 22 carbon atoms are not soluble as soaps because of their insolubility in water. Sodium soaps are generally hard and are called the hard soaps. These are used for washing of the clothes. Potassium soaps, on the other hand, are the more expensive and produce a soft lather and hence are the called soft soaps. They are used for making the shaving cream, shampoo, liquid soaps, etc. Now see what are the synthetic detergents. These day in the place of soaps, the substance which are being largely used as the cleansing actions are synthetic detergents. As the name suggests, they are obtained from the purely synthetic chemicals as compared to soaps which are derived from the chemicals which are obtained from the natural sources like oils and fats. In fact, synthetic detergents are the sodium or potassium salts of the long chain of alkyl hydrogen sulfates or aryl sulfonic acid. Unlike soaps, synthetic detergents can also be conveniently used even in the hard water. This is due to the reason that calcium and the magnesium salt of the detergents, like their sodium or potassium salts, are soluble in water. Hence, synthetic detergents do not form curdy white PPT with hard water. Further, they can also be used in the acidic solution. However, the synthetic detergents have one disadvantage is, unlike soaps, they are not completely biodegradable and hence cause the water pollution. Synthetic detergents are of three types. First one is the anionic detergents. They are so called because a large part of their molecules are anions and they are of two types which are alkyl sulfates and alkyl benzyl sulfonates. The second type of the detergents are the cationic detergents. They are the quaternary ammonium salt containing one or more long chain alkyl groups. They are also called as invert soaps because their surface activity is due to the positive ion and not to a negative ion as in the alkyl hydrogen sulfate detergents. Being more expensive than the anionic detergents, they find limited use. Besides being good cleansing agents, they possess medical properties and therefore they are widely used as germicides in hospital. For example, benzyl dimethyl octammonium chloride. The third type of detergents are non-ionic detergents. They are the esters of high molecular masses alcohols obtained by the reaction between polyethylene glycol and stearic acid. Example is the lauryl alcohol ethoxylate. The composition of the detergent cake. A cake of detergent contains about 20% of the active detergent and equal amount of the sodium sulfate to make up the bulk of the powder. A further of 30 to 50% of sodium tripolyphosphate or the STPP is added as an additive. If the coordinates with the calcium and magnesium ion present in the hard water and thus enhances the cleansing efficiency. Now see what is the detergent pollution. Detergents having the branch chain hydrocarbon chains causes pollution in the rivers and other waterways. The reason being that the side chains stop bacteria from attacking and breaking down the chains. This results in the slow degradation of the detergent molecule leading to their accumulation since the unbranched chains are more prone to attack by bacteria. Therefore, in the most of the detergents used these days, the branching is kept to as minimum so that the detergents become easily biodegradable and pollution is prevented. Now see the cleansing action of soaps and detergents. All the soaps and detergents contain two characteristics group, that is the water soluble, that is hydrophilic, and the oil soluble, that is lyophilic. As a result, one end of the molecule of a soap or a detergent tends to go into the oil phase and other end tends to go into the water phase, with the net result that the material concentrated at the surface of the solution or interface. lipophilic part, that is the chain of the hydrocarbons, and the hydrophilic part, that is the ion. Lipophilic part and the hydrophilic part as shown in the figure. The dirt is generally held to a dirty surface by a thin film of oil or grease. When the dirty water is treated with the soap solution, the non-polar hydrocarbon chain of the soap or detergent dissolve in the oil and grease, and the carboxylate part of the soap or the sulfonate group of the synthetic detergent is added by the surrounding water. This lowers the surface tension between the water and grease. As a result, a stable emulsion of the oil and water is formed. When the surface of the cloth is mechanically scrubbed, the loosened dirt particles are adsorbed by a colloidal soap or detergent particle and ultimately washed away.